Okay, so we've been talking about nomenclature and how to name things, and we talked really about ionic compounds last time. And those are what I refer to as type 1 and type 2 compounds sometimes. And they always involve an ionic compound, a metal, and a non-metal. And as we talked about, really it is that metal that is the most important thing to look at. And that's really what determines whether it's a type 1 or type 2 compound. And if that metal is a type 1 compound, what it means is it has a fixed positive charge. And that's usually our groups 1, 2, 3, silver, zinc, or cadmium here. And when we do have those type 1 guys, because they have a fixed positive charge, we don't have to worry about telling anybody what the charge is on the metal because it can only have one type of charge. So we do use the whole name of the metal. We give our non-metal the IDE ending. And that's pretty much straightforward on that. For type 2, the difference is, again, the metal. And that metal can have a variable positive charge. And that is usually a transition metal. Are just to the right on the periodic table, where we have lead and tin and antimony. And because they do have a variable type of positive charge, we do need to include in our name what the charge is on the actual metal. So we would use the whole name here of our metal. We would add a Roman numeral. And our non-metal will still get the IDE treatment at the end of it. A reminder that, again, the Roman numeral is the positive charge on the metal. Once again, it is not how many metals you have, which is a very common mistake that people make. It is if you took one of those metals by themselves, as we talked about, what the positive charge is. So in nomenclature, pretty much whenever a metal is involved, it really is the one that will pretty much determine sort of how you go about naming these things. Any questions on any of those there? So I think we left off maybe somewhere around here, I think. And that is basically what we just talked about there. So really in an ionic compound and a metal's involved, really the decision is, should I use a Roman numeral or should I not use a Roman numeral? And again, if somebody has a fixed positive charge, thank you, you do not need to use a Roman numeral. And if it has a variable charge, then you do need to use a Roman numeral. The other major thing that we talked about as well is the idea that no prefixes should ever be used in an ionic compound when you're naming it. So that is definitely not the place. So it doesn't matter if you have a bunch of the metals, it doesn't matter if you have a bunch of the non-metals, it will have no effect on the name, and you shouldn't use any type of prefix with those guys. All right. So if we take a look at these guys here as sort of review, we do have Hg, which is magnesium, not magnesium. Huh? I got that lab in my head. Hg is mercury there. Oxygen is a non-metal. So this is a metal and a non-metal together, which means it's an ionic compound. Mercury is a transition metal, and that means that it can have a variable charge. And in this case, we know that that is going to have a +2 charge because the oxygen here has a -2 charge. And remember, mercury is also one of those weird ones. This is mercury with just a +2 and no 2 down here, which means it is mercury 2 in this case. Again, mercury 1 has the 2 on the bottom, as we talked about. So again, if we saw this guy, that is our mercury 1. As it's basically, if you want to think about it, kind of this deal happening here, and that's why there's a 2 on the bottom of that guy. So this is mercury 2, which means this would be mercury, Roman numeral 2 for the charge on the mercury, and this would be oxide in this case. Any questions on that one there? There's magnesium. So magnesium being a metal, bromine being a non-metal. So once again, this is ionic. always want to focus in on the metal. So magnesium is group number 2, which means it has a fixed positive charge, and that's a type 1 compound. And remember, once you identify it as a type 1 compound, and all you have to do is name it, that's all you need to know. You don't have to figure out anything. So we would use the whole name here of our magnesium, and we would give it the bromide at the end. Once again, the 2 here has no effect on it. The reason for that is magnesium has a +2 charge, and each of the BRs have a -1 charge, which is why we need 2 of them to balance it out. That is also, again, the correct formula for the anion, which is Br-, and not Br2-, because that is incorrect. Here we have Li, which is lithium, metal, oxygen, which is a non-metal, and lithium, being group number 1, has a fixed positive charge of +1. That means we just need to use the entire name here of our metal, which is lithium, and oxygen will become oxide. Here, there is no need for a Roman numeral, as that lithium has a fixed positive charge, and there are 2 lithiums, again, to balance out the -2 charge that we see there for the oxygen in this case. Lastly, we have chromium, which is Cr, is a metal, fluorine, which is a non-metal, and chromium is a transition metal, which should automatically signal to you that that is a type 2 compound and can have a variable charge. So we have 1 chromium. We do know that fluorine is group 7, has a -1 charge, and there's 2 of them. And that gives us a -2, which means the chromium here should be +2 in this case. And that would mean that the name here would be chromium, Roman numeral 2, and fluoride. Any questions on type 1 or type 2 compounds here? Okay. So speaking of really another type of compound to name now is type 3 compounds. And type 3 compounds are what are referred to as binary compounds. This is basically going to be 2 nonmetals together. And when we have 2 nonmetals together, as we talked about with bonding, we are going to have sharing of electrons that are happening. And with the sharing of electrons, we actually will name these differently than we do with ionic compounds. And this is actually the appropriate place where prefixes basically happen. So this is the type of stuff that we do want to use prefixes. So there's a table coming up, but like mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, maybe nona is 9, deca is 10, as we go through there. So we do use prefixes here with our nonmetals, and this is really where you should use them. And really the only place you should use them is when you got these 2 guys that are nonmetals together. These are essentially probably the easiest ones to name and write formulas for, but they are also the one that most people screw up on because they want to do all kinds of weird, stupid things. So don't do any of those weird, stupid things. Yeah, it's just pretty much name like it is here. And it should really literally take you a second to name these guys and actually write the formula for these guys, because there's really not much to figure out when you're dealing with these type of compounds. So let's take a look at them. When we have type 3 compounds, they only contain nonmetals, and the way that we basically do it is we use a prefix if necessary, and we use the whole name of the first element in the formula. We then use a prefix on the second guy, and the second one will be named like pretty much a normal nonmetal. It will drop the last part and put the IDE over here. Now, there are a couple of rules that we follow when we are dealing with type 3 compounds, which are nonmetals and nonmetals. Again, you have nothing to figure out in terms of balancing or charges. You just got to pick the right prefix. The 2 major rules is this: mono is not used, on the first name, but it is okay on the second. And the other sort of thing that occurs when we're doing type 3 naming is the prefix will have a vowel at the end, and the first letter of the element will also have a vowel. So sometimes you'll end up with two vowels that sort of back up to each other. Major problem is like when an A and an O sort of backs up to each other in the name, or an O and an O. And these are the prefix ending, and that's like the element beginning of their name. So typically we do sort of cancel out the vowel at the end of the prefix, and just kind of roll with the first letter there of the element to sort of bridge the prefix and the name. So for example, one example here that will cover both of these is something like CO. And C is carbon, which is a nonmetal. O is oxygen, which is a nonmetal. So as soon as you see those two nonmetals together, that should tell you it is a type 3 sort of situation, and we should be using prefixes. And all you have to pretty much do is count how many are there. So there is one carbon, which means the prefix would be mono. There's also one oxygen, which means the prefix would be mono. So in this particular case, we do not use mono on the first name, so we will not use it on the first name. So we will just simply use the whole name of the element, which would be carbon. Here we can use mono on the second name, so we'll use mono, and oxygen becomes oxide. And we get this name, which is carbon monoxide, which is not clearly what we call it. We usually call it carbon monoxide. And that's because we got the two O's to back up. So we do get rid of that O in the prefix. And this becomes what we normally call it, which is carbon monoxide in this case. Question on that there. So like I said, there's really not much to figure out other than what is the right prefix and how many there are. There's no charges because these things are sharing electrons. So you don't have to worry about balancing out anything to zero like we do in an ionic compound. Any questions on that there? Now, what comes first? Well, as we just talked about, pretty much the formula sort of dictates how you should name it. So whatever element comes first in the formula should be first in the name, and whatever element comes second in the formula should be second. And going the opposite way around, whatever the first name is will be the first element, and the second one will be a second. Yeah. Yeah. No, so you could use any other prefix on the first one except for mono. So basically, if you have one of that first element, you just use the name of the element, no mono. But if you had, like, say, two of the first element, then you can use di and tri, and all that's all good for the first name. But just mono itself is not good for the first name, but can be used on the second. Yeah. HO would be hydrogen monoxide if you had that. Yeah. Yes, yeah. Other questions on that? Just like if you had like NO as well, be nitrogen monoxide and those type of things. So we just want to avoid the mono on the first name, but definitely can use on the second. But any other prefix could definitely go on the first name. Other questions on that? All right. So here's a table, and again, similar to the one in your book there, of our prefix that we just talked about. And again, a lot of times we will drop that A as it goes into an O, or two O's that come together. One prefix that's usually okay is if you get a couple of I's that back up together, then that's okay. But really it's the A and the O and the O and the O that you want to kind of drop off of the prefix name. And there's a couple other examples here. Again, tetraoxide here, we're going to drop the A, so we don't get that AO. And then there's our mono example. As we might have talked about last time, there are things that have common names. You should always use them as common names. So once again, H2O is water. Don't call it dihydrogen monoxide. Yeah, so it is water. Should be a free point. Yes, put water and move on. NH3 is ammonia, not to be confused with, as we'll see in a bit here, ammonium. And we had, I think, methane, which is what comes out of your gas vent there, CH4. So you definitely should use the common names for these guys. Again, you should call ammonia ammonia. You shouldn't call it nitrogen trihydride or anything like that. So you should use ammonia for those three. Everything else you could kind of roll with the type 3 naming. I think we also talked about it last time that although hydrogen really is a nonmetal, and when hydrogen hooks up with something like this, say in the gas phase, we do sort of treat it more like an ionic compound than sort of a covalent compound like it is. And we just think of it as like H plus and Cl minus, and we would call it like hydrogen chloride gas. Same thing if I had H2S with a G there, this would be still hydrogen sulfide gas, which you do not want to smell. The reason we have two hydrogens here is because the S has a -2 charge and each of the hydrogens is +1. So although in reality, both of those things are sharing electrons and so forth, there's a reason that these guys usually will kind of end up as acids, and they're sort of treated more like ions than sort of sharing of electrons and molecular compounds. So we do sort of name it more like a type 1 compound. The only place where you would, again, perhaps do a type 3 situation with hydrogen is if maybe it came after another nonmetal. It came second, like if you had maybe like BH3. Here, this would be boron, which is sort of a nonmetal. Hydrogen is a nonmetal. So this would be something like boron trihydride, and we would use the prefix here. But again, if hydrogen sort of comes first in the formula, in a lot of cases, we will kind of mostly treat it like sort of an ion, even though, again, they're sort of sharing electrons in that case. Any questions on that there? All right, so why don't you name these, and when we give you some formulas or names to write the formulas for. So why don't you write the formula for dinitrogen hexoxide. Why don't you do carbon tetrabromide? And why don't we just make up something that maybe doesn't exist? So let's just do like, how about like a trichlorine penta iodide. All right, formulas on the right, names on the left there. Okay, let's take a look. And again, these really should be probably the quickest ones that you do. So when we look at it, we do see I, which is a nonmetal. We see O, which is a nonmetal. So automatically that should tell you it's a type 3 compound, and that is prefixes, basically. I don't have to figure out charges or anything like that. I just need the prefix. So basically 2 is di, 7 is hepta, and then that's pretty much all I need to name this. So this is going to be diiodine. We're going to use the whole name there of the first element. We will use our second guy here, prefix hepta. We're going to drop the A because the next letter there's an O, and that'll be diiodine heptoxide. Here again, the two I's are okay. Mainly that A and O or O and O combination is the issue. Any questions on that one there? Here, CO2, once again, I see carbon's a nonmetal, oxygen's a nonmetal. There's only one carbon, so that's mono. There are 2 of the oxygens, which is di. Once again, we do not use mono on the first name, so we will use the entire name there of the element, which is carbon. And dioxide here on the second. The last one here on the left, we have phosphorus, which is nonmetal. Chlorine, which is nonmetal, which tells us it's a type 3. Here we have just one of the phosphorus, which is mono. We have 3 of the chlorines, which is tri. And once again, no mono on the first name. So we will go phosphorus. And this will then be trichloride, IDE at the end of it. Any questions on any of those names? Yeah. Like I said, nothing really to figure out other than the correct prefix, and just don't use mono on the first one. Drop one of those vowels if necessary. You should be in good shape on those. Yeah. Probably the simplest of all naming, again, is on the right there, but people sometimes do screw it up. When I see this, I see prefix, I know it's type 3. All I have to do is pretty much write what it says. So di is 2, nitrogen is N, hexa is 6, oxide is oxygen. So we got a little something like that, and we are done. Coming to the next one, carbon, no prefix there, but I do see a prefix here, which is tetra. So that does tell me it's type 3. So carbon with no prefix means I just have 1. And that means that the next one is tetra, which is 4, and Br for our bromine. It would look something like that. And lastly, here on my made-up thing, probably here, tri and penta are our type 3 prefixes. Chlorine is Cl and tri is 3. Iodide is I and 5 in this case. And there we go. Any questions on type 3? Yeah. So pretty straightforward, probably the easiest ones. But again, people do want to kind of do weird things. Once again, we do not see any crossover. And what I mean by that is obviously there's no Roman numerals here or anything like that. So prefixes go with where they go. Roman numerals go where they go. And obviously, if you don't need them, then you shouldn't have either. There's very slim chance of that happening. So they should really never cross over. So as we just talked about, speaking of Roman numerals, no Roman numerals, type 1 fixed charge means no Roman numerals needed. Type 2 has a variable charge, which means you need a Roman numeral. And type 3, as we just saw there, is where you should use prefixes. So again, each of those things have the proper place to use them. And you really shouldn't mix any of these things together. Any questions on any of those 3 types of naming there? All right, so a little decision tree if you need. We're then going to talk about polyatomic ions, and polyatomic ions are really groups of nonmetals together, and they are sharing electrons, and they end up having a overall charge based on how they're actually sharing electrons or who they're sharing electrons with. So when we look at a polyatomic ion, for example, here is actually 2 polyatomic ions. We have NH4, NO3. We break it up right about there. We have this guy here, which is NH4 plus. That 1 nitrogen and 4 hydrogens, they are all bonded together. They're all sharing electrons, and it has a +1 overall charge. This guy right here is our NO3 minus. That 1 nitrogen and 3 oxygens are also staying together and sharing of electrons, and basically has a -1 charge. This is really still an ionic compound, which means whenever we have a positive charge and a negative charge, it needs to equal 0. And that's why we just need 1 of each, because that's +1 and -1. These elements will never break apart. We actually drew these when we did bonding. NH4 plus looks like this, where they're sharing electrons. And our NO3 minus was our guy with some double bond action happening there. So it really is these 2 ions coming together. So they are kind of weird things, as they do share electrons, but they do have an overall charge. So they are treated like ions. These guys have special names that go with the formulas. So for example, our NH4 plus is what is known as the ammonium ion. Not to be confused with ammonia that we just saw, which is NH3, no charge. This is NH4 with a +1 charge. This guy right here is nitrate ion. The goodish news about polyatomic ions is we basically just use the name of the polyatomic ion. So regardless of how many you have in a formula, it doesn't really matter. You could have a bunch of them or just one. We just use the actual whole name for the polyatomic ion when we go to name it. So this guy here together would be known as ammonium nitrate. And basically in this case is we have two polyatomic ions, which just put the name together as ammonium nitrate. Now, I will say that probably for the most part, this guy right here is one of the few positive polyatomic ions that you'll come across. There's a few others like hydronium and a couple others, but most of the time the polyatomic ions are negatively charged, which means what usually will happen when you have a polyatomic ion involved is it will really be a metal and a polyatomic ion. So that is most commonly how you'll see these guys together, is as a metal, which would be our positive guy, and a polyatomic ion, which would be our negative guy. So once again, because a metal is involved, as we saw with type 1 and type 2, it is actually the most important thing, even with a polyatomic ion. And it really comes down to a decision of whether or not you should have a Roman numeral or not a Roman numeral. So what happens a lot of times when we have a metal and a polyatomic ion together is we kind of fall back on our type 1 and type 2 sort of rules. So if that metal is a type 1, no Roman numeral is needed. And if that metal is a type 2, you do need to figure out the charge and the Roman numeral. So for example, if we had here NaNO3, that is a metal in our polyatomic ion, which is nitrate. And again, here we would fall to the metal, which is sodium in group 1, and that has a fixed positive charge, which means it's a type 1 compound. And we would just use the whole name of it, which would be sodium. And again, we would use the whole name of this guy, which would be nitrate. And this is made up of a sodium ion with a +1 charge and our nitrate ion with a -1 charge, which is why we just need one of each of these guys. Any questions on that there? It could also be hooked up with a type 2 metal. So for example, if I had FeNO3 2, that is iron, which is a transition metal. That is nitrate. Iron is a transition metal, which means it's a type 2 compound. We do need to figure out the charge on it. We do know that we have NO3- and we have 2 of them here, which gives us a -2 overall charge, which means to balance it out to 0, because it really is an ionic compound here, we would need a +2 charge on the iron, just like we kind of figured out when we did type 2. And the name here would be iron Roman numeral 2, once again for the charge. And even though there are 2 of those nitrates, it will not have an effect on the name, so it will just still be called nitrate at the end. Any questions on that one? Yeah. Why is the 2 not next to Fe? The 2 is because we actually have 2 of the nitrate ions. So we have actually these 2 guys, which are necessary because they both carry a -1 charge to balance out the +2 charge that the iron actually has in this case. So that's why the 2 is there. Also, again, it has no effect on the name, but as you can see in the formula there, I did use parentheses around that polyatomic ion. And that's really important to do whenever you have more than one polyatomic ion. You do need to put parentheses around it and the number on the bottom right to indicate how many you have. And that's because if I did not do that and I wrote it like this, FeNO3 2, that means I have how many oxygens? 32, which is clearly not the case here, as I only have 6 really in our nitrates. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom to indicate how many you have, so people know it's like a whole unit of those things that you have in that particular formula. Any questions on that there? So let's take a look at these polyatomic ions a little bit closer here. So here's a table. Here's another table. That other table is similar to what's in your book. This table is also on Canvas in the exam 2 area. And there's a couple of them, but this one's there in case you want to see it bigger than in the lecture notes. There's a PDF of it as well. Unfortunately, or fortunately, I don't know, however you want to look at it, they do want you to know these things. Yeah. So you do need to know the names and also the formulas that go with it so that you can put it together correctly. So there are ways that you can group these polyatomic ions together to make it a little bit more manageable, and ways that you could sort of figure out how to remember them. So a lot of times people think of these as having groups of 2 or 4. So for example, we saw on this last slide NO3 minus, and there's also NO2 minus. The only difference between each of these is they both have a -1 charge, but it's the number of oxygens are different. So NO3 minus is nitrate, AT. NO2 minus is nitrite. You also look at something like sulfate, which is SO4 2 minus and SO3 2 minus. This is sulfur and 4 oxygens, sulfur and 3 oxygens. They both have a -2 charge. That is sulfate. And this is sulfite. So typically when you look at polyatomic ions and kind of group them by a group of 2, for example, the one with the most oxygens in that group will end in ate, and the one with the least number of oxygens will end in ite. So the one with the most oxygens typically will end in ate, and the least oxygens will end in ite. So how can that help you? So some people will, for example, learn all the eights and know that if I needed an ite, all I have to do is just drop an oxygen off, the charge stays the same, just adjust the number of oxygens. Could also learn all the ites and know if you needed like an 8, you just add an oxygen, everything else stays the same. So you could kind of learn one and know how to sort of adjust from there, up or down, to get what you need and what you're looking for. So for example, if I had CO3 2 minus, that is carbonate, ATE. What would carbonite be? CO2 2 minus, right? It has one less oxygen, so it ends up that way. Just like if I have PO4 3 minus, that is phosphate. And if I wanted phosphite, it should be PO3 3 minus. Again, one oxygen less. So that's a really good way to sort of tackle it without trying to memorize everybody individually. Is to sort of memorize, again, either the eights or the ites, and just know how to adjust the oxygens up or down to get what you're looking for. Any questions on that there? There's also, though, some that are related to each other. There's actually 4 that are related to each other. So for example, it's right about here. What I think I'll do is I'll grab a page somewhere to do that right here, maybe. So if you look on that chart, you will see, for example, ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Now, all of these guys have a -1 charge, and really the only difference between all 4 of these that are related to each other is the number of oxygens. So once again, we could apply our same sort of approach that we've been talking about. If I break them up right about here, everybody to the left has the most oxygens in that group of 4, which means because they have the most oxygens, they should end in what? They should end in 8. Yeah. And so that would make this, for example, chlor8. This guy would also be chlor8. Now, clearly, you cannot have the same name for 2 different things. So when you have a group of 4 that's related to each other, the one that has the most oxygen out of that group of 4, in addition to ending in 8, will start in per. So you'll put per in front of it. So this is what is known as perchlorate and chlorate. If you go the other way, those are the guys with the least number of oxygens in that group, which means they should end in ITE. So going to the right here, this would be chlorite. This guy would also be chlorite. Once again, you can't have those two things that are different in the same name. So when we have a group of 4, the one with the least number of oxygens, in addition to ending in "ite," we'll actually start with hypo as well. So that is hypochlorite. So again, you could still do your adjustments up or down in a group of 4 by just adjusting the number of oxygens as well. First off, any questions on that there? That Cl is a halogen, which means I could swap out that for really any halogen in group 7, which means if I had BrO3 minus, that's not chlorate, but that becomes now Br is bromine, so this becomes bromate. If I had IO3 minus, that is now iodate. So you could do that for any of those guys there. If you swap out the halogen, it's basically named the same, just kind of replace the halogen part of the name with whatever you're swapping it out for. Question on that there? Yeah. BrO4 minus would be perbromate. Yeah, exactly. And just like if you had BrO minus, it would be hypobromite. Yeah, and so forth. So again, the idea of learning these is to actually learn them. And sometimes memorization is straight up memorization works for people, but sometimes it's like overwhelming. It's a lot to sort of try to remember. So again, sort of breaking it up of, I'm just going to remember a certain amount of them and then know how to sort of adjust them up or down is a really good way to sort of do that. In addition, other things that we will see on the periodic table, for example, is you could have something like carbonate. And sometimes we may put a hydrogen or H plus in front of it, and that will make it HCO3 minus. It is not just an H, but the plus is important. That's how the charge changes. So -2 and +1 leaves you a -1 left over. And basically all I did is put a hydrogen in front of it. So it would make sense that we would then call this hydrogen carbonate. And hydrogen carbonate also goes by a very historical name as well that people still use today, which is known as bicarbonate. In case you got some heartburn right about now, some bicarbonate there. We also see this with sulfate and HSO4 minus. So we have SO4 2 minus, which is sulfate. Adding that H plus to it gets us HSO4 minus. Again, the charge is adjusted as well with the hydrogen, and this is known as bisulfate or hydrogen sulfate as well. Any questions on that there? Yeah. Yeah, so the prefix here are the bi, sort of if you're asking about the bi part of it, it's a historical sort of name to it. So it's not necessarily a prefix in that sense. It's just sort of a historical name people kind of still use instead of hydrogen. They kind of use it for in place of hydrogen. Now there are when you look at this chart, there are some polyatomic ions. It's like pirate, there are some polyatomic ions that do have prefixes built into their names, like we see here dihydrogen, we see dichromate, and so forth. So this is the one place where I was talking about earlier where it is possible that you could have a Roman numeral and a prefix together, and it's only because the prefix is actually part of the name. It's not really because you're putting the prefix in, but it happens to be part of the name. So that's really the only place where you could have a type 2 metal with a polyatomic ion that you would have a Roman numeral and a prefix. But again, the prefix is not really because you put it in there. It just happens to be part of the name. And that's the only time that probably should occur together, is that sort of prefix. Now, although a vast majority of these guys do end in either ate or ite, there are some polyatomic ions that end in IDE, like hydroxide is IDE, cyanide is IDE, azide as well is IDE. But again, a vast majority of them will be ate or ite, and that's a really good way to, sort of figure out. So for example, if I had SO4 2-, which is our sulfate, but I wanted persulfate, what should the formula be? Persulfate should be, yeah, one more oxygen up, so it'd be SO5 2-. So again, that is the way that you could adjust these things. All right, so let's take a look at some examples here. We can clear maybe what's on here. And let's just do some here. So what are the names? And I'll leave this chart up here so you can look at it for each of the following here. Let's go with K2SO4. Let's do CuOH2. Let's do NiMnO42. So what is the name of those guys? And why don't you also write the formulas for ammonium sulfide. We'll do iron 2 chlorate. And let's do sodium sulfite. All right, so names there for the guys that are formulas, and give the formulas for the name. Yeah, let's take a look and see how we're doing. So we'll start up here. So we have a metal and we have a polyatomic ion. So once again, it's the metal that's important. So potassium is group 1, which means it's a type 1 metal. So really for the naming, that's all you need to figure out. We're going to use the whole name here of the metal. And once again, our SO4 is sulfate, so we will use the whole name of the polyatomic ion. Here we have 2 potassiums to balance out the -2 charge for the sulfate in this case. Yeah. Any questions on that one? Again, just like type 1 has no effect on the name for potassium. Here we have copper, which is a transition metal, and a type 2 metal. We have hydroxide, which is a polyatomic ion. So here we do need to figure out the charge. We have 1 copper. We have 2 of these hydroxides, which gives us an overall -2 charge. That means in this case, our copper is going to be carrying a +2 charge. And that would mean, I'll just write up here, copper Roman numeral 2 for the charge. And even though there are 2 of those hydroxides, has no effect on a polyatomic ion. We just use the whole name of it, regardless of how many they have. Any questions on that one? Again, we could also see in the formula there, we got some parentheses around the polyatomic ion because we do have more than one of them to get the proper formula. Looking at the last one here, that is nickel, which is a transition metal. That is permanganate, which is right about there. And that means that we would have our nickel as a transition metal. We need to figure out the charge. We have 2 of these permanganates. So that basically is MnO4- twice. So that is a -2, which means our nickel in this case will be +2. And this would be nickel Roman numeral 2 permanganate. Any question on any of those names? Yeah. It's again just one of those polyatomic ions, so you do have to know the charge and memorize them. So permanganate's MnO4- is the formula for it. So permanganate is this guy, which is right there on our chart. And by the way, what would this guy then be? Not permanganate, but it would just be manganate. Yeah. So again, that's how we could adjust down if we needed to from something else. Yeah. Looking at the names here, I'll start on the bottom. We have sodium, which is group 1, so it has a +1 charge. We have sulfite, which means it has the less oxygen, so it's SO2 2-. In this case, to balance it out, we will need 2 of the sodium ions to do so, and that will give us an Na2SO3. So here we actually only have 1 polyatomic ion, so we do not need the parentheses around it. So we just need parentheses if you have more than 1 polyatomic ion. Question on that one? Coming here to the iron example. Iron Roman numeral 2 means that we have an iron with a +2 charge. Chlorate is ClO3 minus. So in this case, we're putting together a +2 and a -1, which means we need 1 more of the -1s in this case. And this will give us a formula of Fe. We do need parentheses because there's more than 1 polyatomic ion here. ClO3, and again, the 2 on the bottom. Any questions on that one there? Lastly, there we have ammonium sulfide. So ammonium is this guy right there, NH4+. Sulfide is actually from the periodic table. That is sulfur, group 6, which is a -2. So in this case, we actually need 1 more of the ammonium. Again, not to be confused with ammonia, which is NH3. Because we have 2 of the polyatomic ions, we need a little parentheses, a 2 and an S in this case. Any questions on polyatomic ions, how to sort of adjust them, figure out what's going on? Like I said, probably 99% of the time, it's going to be pretty much a type 1, type 2 situation. So the major thing that you have to determine is, should I use a Roman numeral or not in most cases? And again, you just use the whole name of that polyatomic ion, regardless of how many you have. Any questions on polyatomic ion naming here? Okay. All right, so we did obviously talk about these patterns here earlier as we were just kind of going through it. But again, per for a group of 4 where there's the most oxygens, and hypo to start that guy that has the least oxygens. Ite or 8 is the ending depending on more or less oxygens. We also talked about, again, you can swap out the halogen and it's named very similar. And also our hydrogen, which is really H+, so you do have to adjust the charge like we see there with our carbonate and our hydrogen carbonate that we talked about. All right. There you go. All right, so we obviously talked about these, so we'll roll through this here. The next thing we're going to talk about is naming acids, and acids are really substances that can produce H+ ions in solution. They are sometimes referred to as protons. We're going to talk about acid-base chemistry, and that is because, as you know, hydrogen has 1 proton, it has 1 electron, and it has no neutrons. And the only way something becomes positively charged is it has to lose an electron, which would leave hydrogen just a proton. So that's why it's sometimes referred to as just a proton. Also, something that we'll come across later on and that you'll see in chemistry a lot, especially when you're dealing with acid and bases, is H+, which is the hydrogen ion, and H3O+, which is a polyatomic ion, which is known as the hydronium ion, are essentially the same. They're used pretty much interchangeably, especially when you're doing acid-base chemistry. I personally use H+ most of the time, but a lot of books will use H3O+ for it. And it's sort of, like I said, interchangeable. It represents really the acid part of the solution. And what makes something an acid is that ability to, when it's in solution, pretty much liberate a free H+ and let it go floating around in the solution. And that is why when we write formulas for acids, they are typically solutions, and they typically should carry the AQ sort of abbreviation next to it, which is the aqueous symbol. And that means that it is a water environment. It's basically a solution. And this is how we know, for example, that we are dealing with an acid rather than something that's not an acid. So a very easy example is HCl, as we saw earlier. If it happens to be a gas, people will call it hydrogen chloride. But if you take that gas and kind of bubble it through some water, it will become aqueous, and you will get an aqueous HCl, which is known as hydrochloric acid. And that is why in a lot of cases, as we were talking about earlier, when we have hydrogen like this, HCl, we sort of think of it like an ion, because it sort of becomes like ions as it releases that H plus from its covalently bonded situation in a solution. It will create ions. So that's why they're kind of named as sort of like a type 1 sort of compound. But acids should have that AQ symbol next to it to indicate that it is an acid. And you should always put that when you're writing formulas for acids. So let's talk about acids and really how we know or how we go about naming acids. Acids, really, it's all about the oxygen. So when we're naming acids, it's about oxygen. So the answer is, if there are no oxygens, your acid name basically is hydro something ic acid. So as we just saw there, HCl is hydrochloric acid. So the missing part is really the negative ion. For all acids, the cation is basically H plus. So for every acid, the positive ion is always going to be H plus, and it's the negative ion that basically determines how you name it. So that would be hydrochloric acid. This is basically H plus and Cl minus. 1 and 1 gives us 0 when we put it together for our formula. This guy then would be HBr is hydrobromic acid, right? That would be basically H plus and Br minus are the two ions that are present. H2S here, that's aqueous. That would be called what? Hydrosulfur, right? So hydrosulfuric acid. So this would be hydrosulfuric acid in this case, yeah. And in this case, we have 2 hydrogens. That is because of the sulfur here. Sulfur has a -2 charge. So we do need not 1, but we do need 2 of those hydrogens basically to balance out the charge for our -2. So hydro is oftentimes used incorrectly when people are naming acids because they want to put it on every acid because it makes it sound more chemistry-like. It is strictly for this type of acid that does not have oxygen. So hydro should only be used when there is no oxygen in your acid. Any question on no oxygen? Yeah. Now, when we do have oxygen involved, and if the answer here is yes, we have oxygen, it will have a polyatomic ion that we just saw. And as we saw, those polyatomic ions pretty much end in one of 2 ways. They either end in ate or ite, and that determines how your acid is named. If the polyatomic ion ends in ate, your acid would be something ic acid. You think like you ate too much, you feel icky. That's a good way to remember it. So for example, here, if we take something like HNO3. NO3 is nitrate, ATE. This would be nitric acid. If I have H2SO4, SO4 is sulfate, which means this would be sulfuric acid. Once again here, the sulfate has a -2 charge. That is why we need not 1, but 2 of the hydrogens to balance out the charge in the formula. Question on that there. Now, if your guy has oxygen and it's an acid, By the way, that is sometimes referred to as an oxyacid because it has oxygen. So that's what that sort of refers to. If it does have oxygen and the polyatomic ion ends in ITE, your acid name will be something OUS acid. So if we take HNO2, NO2 is nitrite, which means this would then become nitrous acid. So this would be nitrous acid. H2SO3. SO3 is sulfite, which means this should be what? This should be sulfurous acid. So sulfurous acid in this case. So as you can see, if it does contain oxygen, it will have that polyatomic ion, and there is no hydro to be found. Yeah, so hydro should not be used with anything that has oxygen in it that's an acid. Any questions on that there? Now, if we go take a look at one down the rules here. There we go. That was our rules we just talked about. So here's a table from your book. Again, these all have no oxygen. They're all acids. And as you can see, they all start with hydro. They end with ic. And again, the middle part there is our anion along the way. And these are some that have oxygen. Again, no hydro to be found, but the ate or the ite determines the ic or the us in terms of how the acid is named. So HF would be hydrofluoric acid as it has no oxygen involved. This would be a little hydrofluoric acid. This obviously is the one we did earlier that has nitrate, which becomes nitric acid. So if you have the name of an acid and need to work your way backwards to the formula, the name gives you a lot of hints as to how you could get to the formula. So for example, if we had, we'll just do this one here, hydroiodic acid. And we'll look at perchloric acid. And maybe we'll do chlor acid. All right, so let's say we have these names and we wanted to go backwards and write the actual formula. The first thing that we should know is if it is an acid, pretty much the positive guy is going to be H plus. So we just need to kind of figure out the negative guy to put it together. So in this case, when I look at this name, which is hydro, that automatically tells me that there is no oxygen involved. And that means that I have H plus and the negative guy is the iodide there, or iodine, which would be group 7. And that would give me both of my guys that I need. One of each gets me to 0. And now I have the formula of what I'm looking for. Question on that one there. Now, if I come to perchloric acid, I see no hydro, which tells me it does have an oxygen. And that means that it's a polyatomic ion. And what I do know is if it has oxygen, it's a polyatomic ion. This guy ends in ic, which means that the polyatomic ion should end in 8. So if you just cross that out and write 8, you now have perchlorate, which tells you that is the negative guy, which would be this guy, along with the positive hydrogen. And now you could get to the formula really quickly by using the name to your advantage. So you could cross out the ic, put the 8 back in case you're not sure what the polyatomic ion is, and then it'll actually tell you what it is in that case. Question on that? Now, if I come over here to chlorous acid, once again, I do not see hydro, so I know it has oxygen. I see OUS, which means my polyatomic ion ends in ite. So if I cross that out, put ITE, that is chlorite, which tells me that the negative ion in this case is this guy. And obviously, again, our positive ion for any acid would be H plus. And now we could put it together in our proper formula. Question on that there. And again, if you could also see that the per stays with the name when you name an acid. Yeah. Yeah, so I would say the proper thing, so I won't say 100%, sometimes people don't put it, but it is proper that you should put it. And sometimes they'll just say, hey, name all these acids, and they won't put the aqueous. So you definitely should write it. If not, you could probably assume it probably is an acid if there's a hydrogen like these guys here. But definitely if it's not, then it could go either way in terms of mostly like something like hydrogen chloride or hydrogen chloric acid or something like that. On the test, I definitely will put aqueous next to it, or I'll say like name these acids and stuff like that. So you'll definitely know for sure. Yeah. Yeah, so that's basically the positive ion is the hydrogen. That's what makes it really the acid, is that H plus is what comes off and goes floating around in the solution. And that's why it's actually, you do need the aqueous because it's actually floating around in the solution. And that's why we do put aqueous. And that's really what makes it an acid, is the ability to release that H plus and start to float around. And that's why it then becomes like ions at that point when it's in solution, because the H plus comes off and then the other guy's left as a negative ion floating around as well in the solution. Other questions? So if we had we have our acids here then. All right. The last thing I was talking about, since we're talking about naming and just with your experiment, which is a hydrate, right? A hydrate's a kind of an interesting thing. A hydrate has two parts. It has a salt part and a water part. And it has an unusual formula like, say, NaNO3 dot 3 waters. This is the salt part, and that is the water part to a hydrate. And they also are written with this little dot between the two, the salt part and the water part. And when we go to name this, we name the salt part just like really a type 1 or type 2 compound. So the salt part there is sodium, which is a type 1. So this would be sodium nitrate. The water part gets like a prefix, like in type 3. So the prefix for 3 is tri. And we name water as a hydrate. So this would be sodium nitrate trihydrate. If you had something like CuSO4.5 waters, this is a type 2 metal now. So this would be copper that has a -2 charge for the sulfate. So it has to have a +2 to balance it out, would give us copper Roman numeral 2 sulfate. And here we would have 5, which would be penta and hydrate. So in terms of a hydrate, we just kind of use hydrate for water when we name it. And we do use that little dot to represent each of those. Like the one you're using today is magnesium sulfate heptahydrate. So this part is the salt. That obviously is the water. And you would do it like normal. So magnesium is that. Sulfate is this. And I would just need one of each. You would put a dot for the water part. Hepta is 7. And then hydrate is water. So you could go backwards and get the actual formula for the hydrate. Question on that there. So bonus material here to try to help a little bit for the lab. Yes. All right. So one important thing is as you go from, say, grams to moles, or even backwards, basically either way. What we do use for that is molar mass. And the molar mass has units of grams per mole. And we could find that on the periodic table. So if we have something like hydrogen here, 1.008, that would be the molar mass of hydrogen. We take it to usually 4 significant figures when we pull it off the periodic table. And that is basically there is 1.008 grams per mole of hydrogen. Or you could use it like a conversion factor in the other way. A mole of hydrogen is 1.008 grams. So if you're looking for the molar mass of some type of hydrate, like say this here, NaNO3 dot 2H2O. Hydrates are a little bit different. You actually have to get the molar mass of everybody that's there from the periodic table. So if you went to the periodic table, you would find sodium, that's 2299. You would find nitrogen, that is 1401. You would find oxygen, that's 16, it says underneath it. And basically we just add up all the parts. So sodium would be 2299 grams per mole, plus nitrogen, which would be 14.01 grams per mole. Again, this is coming from the periodic table. There are 3 oxygens. We take 3 times 16 grams per mole. Now, because it's a hydrate, we do need to include this in the molar mass. So that is another 4 hydrogens. By multiplying those numbers together, we would add 4 times the molar mass of hydrogen. And that 2 also goes to the oxygen, which would be 2 more oxygens plus 2 times our 16. And if we did that with a calculator, 2299 plus 14.01 plus 3 times 16 plus 4 times 1.008 and 2 times 16 gives us 121.0 grams per mole is the molar mass of that entire hydrate. So for example, today you're going to be looking for the percent of water, theoretically. The percent of water would be the mass of the water in that formula divided by the mass of the hydrate times 100%. So the mass of water in this particular hydrate, there's actually just 2 waters, right? And that's just this part of the molar mass. So we just need to take that part of the molar mass, which represents the 2 waters. And if we did that, that would be 4 times 1.008 plus a 32. So the mass of water in my made up example here is 36.03 grams per mole. I divided by the molar mass of everything together, 121.0 grams per mole, times it by 100%. And we would end up with roughly about 29.78% water would be our theoretical percentage of water in this case. So one of the things that you'll have to use is the molar mass, which is that number on the bottom of the periodic table underneath each symbol. It's the grams per mole. And you could use that to calculate the moles of something, the mass of something. With hydrates, though, you do have to include the water when you get the molar mass of it. It's a very common thing people leave off. This is also how we would convert to moles as well, which is the second part of the experiment, which would be helpful maybe as well, just really quick. So as we were looking at our hydrogen, if I had 5 grams of hydrogen, I would use the molar mass from the periodic table and divide by it. And that would give me my moles of hydrogen in this case, whatever it may be. In this case, it would be 5 divided by 1.008. 4.96 or 4.96 moles of hydrogen. So we also use the molar mass to convert from grams to moles, and that's what you need to do when you calculate the empirical formula, like the second experiment. You take the grams, you convert them to moles, and then you divide everybody by the smallest number of moles, and that will give you your empirical formula. So for example, if we converted 2 moles of A from the grams, and we did our conversion into moles, and we ended up with 4 moles of B at this point, what we would divide by is the smallest, which is 2. So you would divide by 2, and that would give me 1 mole for A, and that would give me 2 moles for B, and that would be our empirical formula. Basically it would be AB2. So you'll use the molar mass to take the grams to moles, you'll divide by the smallest number of moles, and we'll give you ideally a whole number, and that will tell you your empirical formula, which is the simplest whole number ratio. Any questions on that bonus material?